This is the walkthrough video for PCTC 2023, round 2, question 12, wall smashing. Okay, so this time we're given a grid, and we essentially have to traverse from the top left to the bottom right by only going on the zeros, or we can smash through a single thickness of a wall, but we want to minimize the amount of wall smashes that we have to do because we get too tired. So this question is kind of like a standard graph question, but with a slight twist, and that twist makes it a lot more difficult than a standard graph question. Okay, but what is the easy bit is the input. So let's input our side length first, and then let's create our grid. So our grid is going to start off as an empty list, and then for as many times as our side length, we're going to take in an input and add that to our grid. Okay, so now our grid is just a list of strings, where each string is a row of the input that we're given. Okay, so what are we actually doing this time? So I'm probably going to not necessarily explain every single part of this problem. And so if at any point you get a bit confused or it doesn't make sense because you've never come across it before or this idea before, then feel free to pause and have a play around or Google a bit more about a specific command or something. But anyway, so what we do in a normal BFS is we don't really prioritize the order in which we look through each of our states in our queue, right? We kind of just go from left to right, which usually ends up being how far deep we are, right? So the metric we look at in BFS is how far we've moved. So and the reason that is because with BFS we can kind of think of it like we move everything one step forwards at a time. So we move all of our routes that have, so like if we've moved, say we have multiple routes where we've moved 5 units, then our BFS is almost like going to move all of those multiple routes to 6 units before it ever encounters a route that moves to 7 units. So what I'm trying to say is that a BFS kind of prioritizes what to check based on the distance you've moved so far. But that's not what we want to do in this case, because as it tells us that the fewest steps possible is not as important as the fewest walls possible. So in this case, we don't want to prioritize distance. We want to prioritize the fewest amount of walls, we want to break as few walls as possible. And that means that BFS is not necessarily possible as a solution to this problem. And so how do we prioritize something that isn't the distance? Well, we have to use a different data structure, and this is called a heap. So to use a heap in Python, we use this library called heapq, and from heapq, we're just going to import everything. And I think there are only going to be like 2 commands we use. Let's just import everything. And so this heap structure, it's almost like a normal list, right? But it prioritizes the order of the list based on the number that you want to prioritize. So a list, for example, the order of a list is just whatever you add to the list or whatever you remove to the list in that order. Whereas a heap, the heap constantly changes its order so that it fits to the priority that you've given the numbers. So it's always constantly sorted. You can think of it as a heap, as a constantly sorted list. So let's create our heap, and what should we call it? Let's call it states, because that's what it is. So it's a state. And a heap, we can just essentially, like a heap we don't have to specifically define, right? By default, if we have one element in a list, Python's going to say that's fine, that's a heap, right? So we don't have to specifically define a heap. If you want, you can write heapify, which converts something into a heap. But if you only have one element in your list, there's no point turning it into a heap, right? Because if there's only one element in your list, it's already pre-sorted for you. Like heapify doesn't have to sort anything, right? There's only one element. And what's that element going to be? That's going to be our state. What's our state going to be? Well, the top priority thing is the amount of walls we've cut down, which obviously starts off at 0. Second priority thing is the amount of steps that we've gone, which again obviously starts off at 0. And that's really the 2 metrics we want. And then of course we also want to keep track of our current coordinates. So we start off in the top left, which is 0, 0. And so let's just make this clearer, because like this is just 4 zeros, which doesn't really make much sense. So let's write them down. So that's walls broken, steps taken, x coordinate and y coordinate. I guess the other way around, y coordinate and x coordinate. Yeah, the order of the coordinates doesn't really matter as long as we're consistent. And now let's create our visited set, and just to make sure that we don't visit the same coordinate multiple times. And this should speed up our code to make it more efficient. Okay, and let's say while states. So whilst there is a state to check, let's keep checking our states, and let's extract them. So let's say walls steps x and y is going to be equal to. So if this was a BFS, you may see me do, for example, states.pop left, because this would be a queue. But this is not a queue, so we can't pop from the left like that. So to take out the smallest value, which is like how the heap is ordered. To take out the smallest value or the smallest state from our heap, we use the command heap pop. And in the brackets of heap pop, we put in the variable name of our heap, which is states. And so what this does is we'll just pop out the smallest element or the smallest state from our entire heap, which is what we want, right? Because we want to be prioritizing the states where you've broken through the fewest walls and the fewest steps in that order. And so that's why we're using a heap. And let me just make sure I fix that typo. It's heap and then pop. And so there are two P's. Okay, and now the bit that, again, we always see in the BFS, we need to check if we visited this coordinate before. So if you visited X and Y, then let's just continue this while loop and not do any computation. And of course, let's also add our current X and Y coordinates to visited sets so that we know we visited it and that we shouldn't visit it again. Visited.add that. Okay, and the final thing we should do before we get into the real computation is figure out if we've reached the end. And we've reached the end and we've solved the problem if we're at the bottom right coordinates. What's the value of the bottom right coordinate? Well, that's just going to be x value side of -1, and the y value is also side of -1. So if x and y is equal to side of -1 and side of -1, then we know we've reached the end, and so we can just break out. But actually, what we want to do, we want to print off the amount of steps that we've taken. And so let's print off steps, and then we can break out of this while loop. Okay, so pretty much, well, a lot of the code is done at this point, but now we're going to move on to the really, really difficult bit. So far, it's been kind of challenging if this idea is new to you, but now we're going to go on to the really challenging bit, which is essentially to try and look for, it's the implementation bit, is to look for which cells we can move to next, and therefore add that to our states heap. So far this has been an algorithmic challenge. Now we're on to the implementation challenge. Okay, so I'm going to do this slightly differently to how I usually do it. So if you've seen me code a problem with a grid before, you may be quite accustomed to the way I code it, but this time it's going to be different. And this is probably the way I say more people do it, to be honest. Even the pros. The pros do it this way and not the way I usually do it. So let's say for x change and y change in that. So what this is, we're just creating this for loop that essentially goes through each of these small for tuples, and it assigns the first number to x change and the second number to y change. And the reason we're doing this is that you recognize that all of these tuples, they represent the change in position if you were to move up, down, left, or right. Because those are the 4 directions we're allowed to move in according to this problem. Up, down, left, or right. And so this represents the x, this represents the y, this represents the x, this represents the y. So, and those represent the changes, right? So if we were to add this to our x coordinate and this to our y coordinate, we would to move downwards. If we were to do the same thing here, we would to move rightwards. Same thing here, would move leftwards, and same thing here we'd move upwards. So this is just a way of going through each of our 4 directions. Okay, and what we should probably do is let's create a new variable. So new x is going to be equal to whatever our current x is from all the way up here from our state plus x change, because x change is just the direction which we're moving in. And the same thing for y. New y is going to be equal to the y from above plus y change, which is just the direction that we're moving in. And now before we do anything, we should probably check to see whether this is actually a valid move, right? Because like we might just be moving off the grid, and you can't move off the grid. And so let's check to make sure we're still in the correct bounds. So if new x is bigger or equal to 0 or smaller than side, and if new y is also smaller than side and also bigger than or equal to 0, then it's valid, and therefore we can continue with the code. So what do we actually want to do at this point? We want to check to see if our new coordinates, so new x and new y, if our new coordinate contains a 0. And if it is a 0, we can just move straight into it, easy peasy. So let's do that. So if grid new y, new x equals to 0, then we can just move straight into it. So to our states heap, we can add the state walls because we haven't broken through any walls in this extra step in this current step. We have taken an extra step, so let's do steps +1. And what are our new x and y coordinates? That's just going to be new x and new y. And we want to add the state to our heap. And to add something to a heap, we do heap push, and then inside these brackets, and then we have extra brackets, and then inside these brackets, we do the heap name, so that's states, comma, and then we do the thing that we actually want to add to our heap, which is this tuple. Excellent. So now, what if the position is not a 0? So what if it's a 1? Then we can break through the wall and go to the other side. But we can only do that if the wall is of thickness 1, right? So we can't, for example, break through this 3 thickness wall. We can only break through this 1 thickness wall. And so to check this 1 thickness, we have to almost move in the same direction again, and check to see if that's a 0, right? So we've moved here, we've seen the 1, and now to check to see if this is a valid wall to break through, we need to move another position to this 0 and check if that's a 0. So let's take in our new x and let's add x change again. So and do the same thing for y. So we're just moving in the same direction again. And now let's check if grid new y and uy and new x, if this is equal to 0, then this is a valid move. So then we can almost just copy this line of code, right? But whilst we have gone an extra step, and whilst we have now saved our brand new x and y variables, we've also broken through an extra wall. So let's add one to our walls value here. And one thing we should also do is, because we've changed the coordinates again, and we've moved the coordinates forwards again, we might again be off the grid. And so we should apply this same check as we did before to make sure that we're that we're still on the grid. And only if we're on the grid do we bother doing the rest of this code. And I think that should be it. Yeah, let's submit that code. I might have missed something, but it seems right. Yeah. 10 out of 10, awesome. Yeah, so I guess the thing to note with this code, I guess, is, or the question, is that this would be a simple graph algorithm or straightforward classic graph algorithm, but because we're prioritizing something that isn't the distance, we're prioritizing a cost. This is like a Dijkstra's algorithm. I think you spell Dijkstra like this. I can never spell Dijkstra correctly, but it's an algorithm called Dijkstra, or Dijkstra, however you pronounce it. I also can't pronounce it. And that algorithm is basically just a BFS, but where you're doing your algorithm where you prioritize something that isn't the distance. So you prioritize a cost. And in this case, our cost is the walls that we break. And so that's going to be our very first number in our state, right? Because the heap automatically sorts from left to right of our state. So the most important value should be on the left, and the least important value should be on the right. And then otherwise, yeah, what we did is we kind of just did the standard stuff up here. And more importantly, down here, we used probably the most efficient way we could to code this to check whether the next move is valid, and more importantly, whether if we have a wall, can we break through that wall? And we just counted for the edge cases where if we, for example, gone out of bounds, and bearing in mind if we kept that in both cases, like whether we break through a wall or whether you don't break through a wall. And yeah, that's just the code we wrote. And oh yeah, that rounds off this series for PCTC 2023-24 round 2. Hopefully you learned a lot through this series, and hopefully you enjoyed that.